Hello and welcome. Well, this is actually the December uh, Anglo-Irish Astro Geeks. I nearly got it wrong because I've been doing the Comic Watch show with Neil just yesterday.
Mm-hmm.
So in reality, it's the 7th. Well, no, actually, it is the November one because we recorded an earlier interview. So I'm wrong. It is the November issue. So without further ado, we'll all introduce ourselves. My name's Nicky Vetts.
I'm Anne Dunn from Astronomy Ireland.
I'm Susan McKeown, Ireland.
I'm Neil Norman from somewhere in England.
I'm Caroline Geraghty from the North Coast and for Astronomy Ireland.
Welcome, Caroline. So, without further ado, we will let Anne get on with the show notes.
Okay, well, I'm a bit early with this, but I just thought we have to get ready for the Geminids on December the 14th. It's the best meteor shower of the year, and it's going to peak on the Tuesday morning of December the 14th at 7 a.m., which is, like, it's getting bright then, but going on all night. Sorry, the moon will be pretty bright that night. It's like 79% sunlit in the sky all on the Monday night. And it'll set around 3 a.m. on the Tuesday morning, and we'll have dark skies then until 7. But that doesn't mean you can't see it before then. I remember being at a party a good few years ago in the days before COVID, and we all went outside to watch a really spectacular display. You need to wrap up well if you're going outside, and maybe lean back on a deck chair unless you want to get a sore neck, which I got during the Perseids in August. The Geminids are produced by debris left behind by an asteroid known as 3200 Phaethon. Am I pronouncing that right, guys?
Yeah,
absolutely.
Guys? Yeah. It was discovered only in 1980. So, and if you don't get to see them that night, don't worry, because they'll be around for at least another week afterwards. And don't be disappointed if it's cloudy, because you might even get to see them through the gaps in the clouds. And I saw them once a few years ago where that one streaked through and actually lit up the clouds from behind. So you have a good chance. They're a good shower. But before that, back to November. The 19th is a Friday, so it's a good night for viewing, and you're going to see the full moon rising with the Pleiades very close above it, with Hyades and Aldebaran below. So like a nice, possibly all in the one shot if you're getting photographs. November the 25th, you can see the moon only slightly waning. It's 72% high in the south before dawn. Now, for those of you who don't want to stay up all night on any night for the next for ages now, Orion has been dominating the southern skies at a reasonable hour, and it looks absolutely amazing with Sirius twinkling below. So anyone should be able to spot that. It's so easy to spot. Jupiter, in particular, but Saturn to the west of it, are brilliant at the moment as well. If you have a look, Jupiter and the moons at the moment are really nice to look at, and again, something nice for people who don't want to have to stay up too late. And then, will I carry on with this little bit, or would you like to say it, Nick?
Well, Neil and I are going to discuss the comet, which is really exciting a lot of us. That's C2021A1 Leonard. The really nice thing is it has the potential to be naked eye. So we've been looking at the history of this comet. It's currently at a magnitude of 9.3 as of November the 11th, and Michael Yeager. It will approach to the Earth down to about 0.2 astronomical units in December, and it's expected to brighten up to Mag 4. Now, big numbers, positive numbers are dim, negative numbers are extremely bright, just to give you the idea. So in the northern hemisphere, it's going to be visible in good condition for a long time, and until December. And while the comet is brightening gradually in the southern hemisphere, it won't be observable until mid-December. Now, a lot of the information Neil and I use comes from our good friend Seiichi Yoshida. He has a brilliant website, both in English and Japanese. If you're really interested, I'll put a link into the show notes, and I'm going to hand over to Neil at this point.
Yes, well, you mentioned it getting up to magnitude 4, but it's really looking like we might get a little bit better than that, because we will be subjected to it having forward scattering, which is basically the comet will be at an angle between the Earth and Sun, but it will be sideways on, and as it's such a dusty comet, it will enhance the brightness. So we're now thinking it could get up to magnitude 2 or maybe a little bit higher. I was looking at another light curve today by Charles Bell, and it could actually get up to 0. It's going to be very low, but it's showing a nice tail. It's on an orbit that is 80,000 years long. It was last in the inner solar system 80,000 years ago. But because it's going to be making very close approaches to Earth, as you said, Nick, which is basically the Moid value for the Earth, so we're very lucky there. That's the minimal orbital intersection distance, for those who don't know. And then it's going to be passing on to Venus very quickly afterwards and making a very close, I think it's 0.02 astronomical, to Venus about 6 days later or something like that. And then eventually, after it makes perihelion, on the 3rd of January, it will be kicked out the solar system. It will pick up enough momentum and be thrown out the solar system altogether.
Well, the interesting thing about this comet, it's been inside the orbits of Neptune since about May 2009. Now, using the epoch of 1950, you have two epochs which we use in astronomy. One's 1950 and the other one is J2000. So this was done under the epoch of 1950, which is well before the comet entered the planetary region of the solar system. Now, the barycentric orbit solution suggests, as Neil pointed out, is roughly an 8,000 year orbital period. So it's 80, thank you. So therefore the comet has spent about the last 40,000 years inbound from approximately 3,700 AU, that is 550 billion kilometers. So the barycentric orbit will remain hyperbolic until will remain hyperbolic after September 2022.
That's right, yeah.
Unfortunately, this is going to be kind of like Borisov. It's a once in a lifetime opportunity, and unfortunately, it's never going to come back.
But we've got a very limited period of time to see it, because it's on a retrograde orbit, which means it goes around the sun the wrong way to the planets. Now, we had that last year with Neowise, and basically that means it will not be very high in our sky when it's at perihelion. So I think I was looking at it earlier on today, and I think it's I did make a note of it. We're only going to have between the 30th of November and the 11th of December to see it, and it's going to be best seen in the morning, around about, say, 5 o'clock in the morning, because then it's going to be quite high, 50 degrees up in the sky, because the moon will be out of the way. If you was to try and look for it tonight, for example, where there's nearly a full moon, or like on Friday, as Anne said, there will be one, you won't see it, because the moon sets as the sky brightens. So we only have 11 days to see it from the northern hemisphere before we lose it, and it goes to the southern hemisphere, and it won't be very good from there, I'm afraid. It should be about magnitude 5, I think, by the time it reappears after conjunction with the sun.
And of course, the other thing is, on the morning of the 6th of December of this year, the comet will be about 5 degrees from the star Arcturus. On the 14th of December, it will be 14.7 degrees from the sun. So it could quickly, it would definitely be better seen from the southern hemisphere by that point. Now, I actually I have managed finally to get an image of this comet about a couple of weeks ago, but it wasn't really that high. Now, I was imaging out of Mount Taylor in the Canary Islands. I may have an opportunity to go for it once it goes south from Chile, but we'll have to wait and see.
And the good thing is, at the moment as well, it's actually showing a forked tail. A lot of pictures are also showing it to be very diatomic carbon rich. It's got a very green coma, but it's got a forked tail at the moment, so it's very active indeed. So I think it's producing around about 300 odd tons of water per second.
Sounds about right.
Gas. Yeah, and the gas production is about 922 kilograms per second. So that's pumping off some dust.
Wow.
Well, as I say, it's Jupiter's orbit is 5 AU from the Sun, and
Yes.
pretty much that's the frost line where methanol at CH3OH and water will start to sublime in a comet.
Yeah.
And of course, this is the first comet discovered in 2021, and to have a retrograde orbit. It's not normal, really, for a comet to do that.
And of course, I think its actual inclination is around about 138 degrees to the ecliptic. Any comet that's over 90 degrees will be retrograde. Anything under will be prograde. It goes around the sun the same way as the Earth and planets do. For example, Halley's comet, I should say, is a retrograde comet, isn't it?
Yeah, it's one of the rare ones.
So, yeah, they're a lot more rare. As I say, the last one we would have seen would have been Neowise, but they are notorious horizon huggers because when they come into perihelion, I'm afraid, so nobody ever gets to see them as good as we should do. But
Well, the inclination of this comet is about 132.68 degrees, and the node is at 255.86. And that's an interesting. The peripesis, the argument of peripesis, is 225.09 degrees.
yes, I mean, as I say, I mean, it's definitely going to be worth looking out for. I don't know. I was just thinking there for a second when it would come into the sort of like the Soho. I believe it's in the Swan imagery at the moment, but I was just wondering if it will be getting close enough to be seen in the Soho images.
Okay, so just to
C3
explain,
or C2.
yeah, just to quickly explain a few things. The longitude of the ascending node is one of the orbital elements used to specify the orbit of an object in space. So it's the angle from a specified reference direction called the origin of longitude to the direction of the ascending node as measured in a specified reference plane. So the node is actually the point where the orbit of the object passes through the plane of reference. Now, so basically commonly used reference planes and origins of longitude include geocentric orbits, Earth's equatorial plane as the reference, the first point of Aries as an origin of longitude. In this case, the longitude is also called the right ascension of the ascending node. That's an angle which is measured eastwards, as seen from the north, counterclockwise from the first point of Aries to the actual node.
Yeah.
Like, I could probably scare you with mathematics at this point. But another one word we have used here is the argument of peripresis. It's also called the argument of perifocus or argument of pericenter. It's one of the orbital elements of an orbiting body. Parametrically, is the angle from the body's ascending node to its peripesis, measured in the direction of motion. I will put links into the notes about these terms just to really help people understand what we're talking about. Yes, it is terribly geek stuff, and of course the orbital inclination measures the tilt of an object's orbit around a celestial body. It's expressed as the angle between a reference plane and the orbital plane or axis of direction of the orbiting object. Sorry?
It's a very cool language.
It's geek.
Yeah.
or as one person who I know very well says, "You're talking Stark," and I say, "Which one, Tony or Nathan?"
Yeah. Yes. I was using the COGS data earlier on today, and I was getting the diameter measurements made by observers, and I translated that into a rough size because it's around about 1 astronomical unit away from Earth at the moment. It transpires that the coma is around about now 164,261 miles in diameter, which is pretty big. So it's very active, and it will get bigger. So I mean, just for those who maybe want to go out and have a look at it, it's basically underneath the Big Dipper, and I'm sure Nick will put some finder charts up, or we can send you to the right places to find them. But you can use now, I think, 10 by 50 binoculars. I think Carl Hergengrother picked it up in notes. Certainly a small telescope will do the job. And it's, like Nick said, a once-in-a-lifetime thing. This thing is never coming back into the solar system, ever again.
I was going to say something now, Neil, and I can't remember what the heck it was.
Yeah. Something technical.
Probably something very technical, yes.
Can I ask a
Explain.
technical question? Like, intuitively, when you go minus something, you think that's going to be less bright. How come plus is less bright and minus is more bright?
Good question. Nick?
Okay, so we're talking magnitude here.
Yes.
This 1 second, because I'm going to try and pull up a simpler description than what I would normally give.
Well, we know the sun is like minus. We always say the sun is minus 26, don't we?
Yeah.
And Venus is minus 4.4. It's a bit like a golfing handicap thing, isn't it? It can be equated to that, can't it?
Okay, so
Is it not?
Space and golf, that works for me.
Yeah.
well, yeah, Apollo 11.
Go on, Nick, hit us with some...
Just give me a second because I'm trying to type quietly.
Okay, we depend on... So, shall we explain forward scattering, or did we cover that, or okay-ish?
Okay.
Because the Earth will be crossing the plane of the comet. Oh, carry on, yep.
Yeah. So, in astronomy, magnitude is a unitless measure of brightness of an object in a defined passband. This is obviously referred to visible light. So, basically, what happens is, because of some of the distances involved, a very, very bright star will still appear to be dim. So the scale is reverse logarithmic. The brighter an object is, the lower its magnitude number. So a difference of 1.0 in magnitude corresponds to a brightness ratio of about 5. I won't go to that math part because that really will confuse people. Or about 2.512.
Yeah.
So an example is a star of magnitude 2.0 is 2.512 times brighter than a star of magnitude 3. So basically, the larger the number, the dimmer the object. The smaller the number, the brighter. The obvious being the sun, which is at minus 26.
Yes.
Great. Oh no, I get that. That's really clear, actually. Seriously, well done.
Now, but we've got to mention the actual comet. That reminds me of Leonard. The absolute magnitude of comet Leonard is 5.3. So, Nick, would you like to explain the absolute magnitude?
No, you go for it this time, Neil. I did it last time.
Okay. Well, when we do comets and things like this, we use a thing called absolute magnitude, and it's worked out very cleverly by these, systems nowadays. But basically, it means that a comet has a magnitude of 5.3 as an absolute magnitude when it is 1 astronomical unit away from the Earth and the Sun at the same time. It would appear in your sky as magnitude 5.3. For example, Hale-Bopp was, I believe, 0 or just under, I think.
Yeah.
But it never actually came that close to Earth, did it? It just sneaked outside. But Hyakutake was a very bright comet. People may remember from '96. It was like magnitude 0 in the sky, but its absolute magnitude was 8. So had Hyakutake been 1 astronomical unit away from Earth on that date, it would have been magnitude 8, and you would have needed a small telescope to see it. But because it was so close to Earth, 0.01 astronomical units, I think, off the top of my head, it appeared as magnitude 0. That's when it gets complicated.
Okay. Here's another good example for you. As we said, the apparent magnitude of the Sun is actually minus 26.74 magnitudes.
Yeah.
The mean magnitude of the full moon is minus 12.7 4. It's dimmer. So the sun is about 400,000 times brighter than the full moon.
Exactly, yeah. And then you can work out how many times it is brighter than Venus, how many times it is brighter than Jupiter.
Yeah.
And then how many times brighter, and imagine the mathematics involved, how many times brighter is it than Neptune? So the sun is minus 26, Neptune is, and then we've got to do this, times it by, divide it by, and then have a nervous breakdown.
Well, think about it this way. If you have very good eyesight and you are very well dark adapted at night, you can just about make out the smudge that is M31, the Andromeda Galaxy.
Yeah.
But it's a smudge because of the sheer distance, which is something like 220 million light years. So you're looking that far back into the past as well. But your eyes on their own aren't that brilliant at seeing in the dark. So an animal would probably be able to see it, like a cat may be able to see it slightly better.
Yeah.
So that dim smudge called the Andromeda Galaxy is probably something like magnitude 22 or something. It's dim.
Mm-hmm.
And of course, because of the distance, light takes that time, and there's so little of it by the time it gets through the atmosphere to your eye. That's why you basically, you can say I've seen the Andromeda Galaxy with the naked eye. You've seen a dim patch.
Yeah.
It's roughly the right shape in the right place.
Yeah.
So that's why you have
Just talking about... Sorry, Nick, carry on.
That's why when you go out to watch a meteor shower, you have to give yourself at least 30 minutes for your eyes to adapt to the dark. And then keep your mobile phone switched off and make sure there's no lights on behind you.
Yeah. I was just going to mention one other thing about the comet very quickly, is a lot of people, because it's going to be quite bright, people are going to be taking images of it, it's going to be on the news and things like this and in magazines. You'll see that it will probably look, like I said earlier on, with a green head and all of this sort of thing. Your eyes will not see that in a telescope because cameras are a lot more sensitive and they can pick up the colours in comets where the human eye cannot. So in fact, I've only ever seen colour in a comet about 2 times, like green. Like I think Vertinen in 2018 was greenish because it's so close to Earth and you could actually visually see it. But the comet will just look like a grey smudge, hopefully with a little tail. So don't expect to see lots of glorious colours.
I remember seeing that comet and it was absolutely beautiful. You know, we got photos of it. You know, and to see, you know, how far away, you know, outer space, for people to get to see something like that with naked eye, it's just incredible.
Yeah, absolutely.
It's a shame.
Mind
It's a shame that we didn't have a comet because, as me and Nick talk about these things all the time. I mean, in 1983 there was a comet called Iris Raki Alcott.
Yeah.
And it was actually it went across the sky. Everybody who saw it at the time, I didn't, but everybody said you can actually visually watch it moving in the eyepiece of a telescope. That wasn't anything to do with the Earth. It was the comet was so close to Earth you could actually visually see it tracking across the sky. And I've forgotten what Jim Scotty said, how many degrees it travelled in a day. I don't know if you can remember, Nick.
I don't, but I think it was several degrees each day.
Yeah, it was shifting, wasn't it? You know, you could visually see it moving.
Yeah.
So,
Incredible.
yeah, when you see things like that.
In fact, that comet holds the record as being the first comet to be imaged by an infrared satellite in orbit.
Yeah.
Because the IRAS part of the name refers to the IRAS telescope, space telescope, which was an infrared imaging scope. Its real purpose was to look back into the dim past of the universe.
That's right.
But they actually caught the comet with the telescope. They reported it at the same time as Geraghty and Alcock did.
Yep.
And the rest is history. So it's the first one to ever be picked up by a satellite. And it's still one of my favourites. Somewhere I've got a copy of the Patrick Moore the Sky at Night about it. It was a fascinating show.
Yeah. Yeah, it was a very nice comet. It didn't have very much of a tail though. It was very dust depleted.
Yeah.
I remember doing some research on it, and it last turned around the inner solar system in about the year 927 AD, and it was on the opposite side of the sun. So we happened to be in the right place at the right time in 1983. Otherwise we would have missed it. And we won't be talking about it right now.
No, as I say, we got lucky. We had the IRAS satellite up there, and George Alcock.
Yes, from his
living room with a pair of massive binoculars found it.
Yeah, and that's what he used to do. Everybody who listens, you must learn the sky. He used to look for comets in the Milky Way, which is, you know, if you've ever looked at the Milky Way with a pair of binoculars, it's to look for a tiny fuzzy object is virtually impossible unless you really know your stuff. So, and he used to do it in his comfort, like you said, in his armchair in his front room. So crazy. And he discovered about 3 or 4 comets, I think, 1953, 56 or 54, something like that.
Just so you can perhaps understand a bit about the comet itself. It's a long period comet. It's about an orbital period of about 970 years. It was discovered in April 25th, 1983. And it was one of those really, really lucky finds. Its moid with the Earth was 0.005.83 AU. That's 872,000 kilometers.
Hey guys, for people, you know, like for amateur observers, you know, wouldn't maybe have, you know, it's quite expensive, you know, to go really up in technical gear, you know, to track these things. You know, there's a certain amount. But what would be the best, you know, the telescopes that you could maybe link into, that while these events are happening, that you could link in real time and get, you know, images to kind of edit yourself?
To be honest, I would say something at least from 6 inches upwards for reflectors or Dobsonians. A lot of the online telescope communities like SLU will be following the comet. So you can take a picture with SLU, places like SLU. They're not the only place you can do it. But the other places like iTelescope, you do need to understand about image processing. But with a DSLR as the minimum, you can do that. I know some people have actually done it with their mobile phones, but you have to have an eyepiece adapter. And as I say, really you do need, for a comet, you need to have what they call go-to, which will move the telescope in right ascension and declination and track the object you're trying to image.
Yeah. Very important.
But here's an interesting thing for you, Neil.
Hello.
Going back to Geraghty Alcock again for a second.
Alcock.
It's the parent comet of the minor Eta Lyrid meteor shower.
That's right. Yeah. And of course, we had a new. We must talk about this. We had a new meteor shower this year, didn't we?
Yeah.
It's the Arids, which is due to the comet 15P Finlay, I believe, Finlay. But that's going to be unpredictable for the future because it's a brand new shower and they pull in and out. But I think we've spent a lot of time talking comets, otherwise this is the Comet Watch, isn't it? We better talk about something else like Aurora and get our guests to dazzle us with the Northern Irish night skies. And drinking venues.
Yes, the local taverns.
I think
Yes,
at this point we'll hand over to Anne and Susan.
Yes,
and
let's
so
go,
they
let's go.
can chat with Caroline.
I'm going to have a pint of wine. I'll be back in a minute.
Well,
Susan,
like,
Yeah.
enjoy your pint, guys.
Yeah, thank you very much. I'm going to have a sausage roll too and a pickled egg.
Yeah.
They
Yeah.
crack you.
We had a nice aurora there on November the 3rd, and it was quite far south. Caroline actually went out to have a look at it, but it was seen in UK and Ireland, Sweden, the Netherlands, and so it started out, there was a sunspot region 2891. It was facing towards the Earth when it erupted with the long duration M1.7 coronal mass ejection, which is CME. And these are kind of bubbles of hot gas and magnetic field. The solar wind picked up and it arrived here faster than predicted, and it hit us at 700 kilometers a second. The energetic electrically charged particles, which were mostly electrons, were accelerated along Earth's magnetic fields into the upper atmosphere, and there they collided with gas atoms. The excited gas atoms were lit up then, and the most plentiful gases that are in our atmosphere are oxygen and nitrogen. So when the atoms are excited, oxygen gives off that familiar fluorescent green that you see in those beautiful aurora pictures, and sometimes yellows. And then nitrogen causes the blue and red colours, and sometimes pink. Although a different sort of oxygen can give off a purple colour higher up. So basically it's our magnetosphere. We're just a big giant magnet really, and we have magnetic bubble around us. So the solar wind comes along, is channeled down, I'm going to tell this real quick, channeled down through the magnetic field lines, the poles, and occasionally it goes on out past the end of the magnetosphere, and then it kind of snaps back, and we get a second burst. So Caroline actually was out having a look for it, and would you like to tell us how you view it, and maybe tell us about etiquette about viewing auroras when you're out in a dark spot?
Yeah, well, that one you're talking about, early November, we actually only got a slight cloud break, so we just seen a little bit of green, but it was amazing, that how it spread, really worldwide, hitting parts of places, Canada, America, places that would never really get a strong aurora. But it was in the 17th, I think, of September. Now normally we always do a little drive out most nights to the mountain. Then recently, with Hayden, we got to talk to Adrian Madut, the French astrophotographer who chases the aurora. And with the questions we were talking to him, we know the basics of what to follow and what to look for. And it all the penny kind of dropped. And this night, it was Friday night, was it the 16th, 17th of September, one of those. And I just happened to, we always keep our camera charged up. We always have a tripod ready. We're like a doctor, with the bag, you're on the call. So that's the way we are. But this night, we happened to look at the stats. Now there's a lot of brilliant aurora apps that you can follow. And the one that we go by is Glendale Sky Aurora, because they are closer to us, the Shetlands. So where we are on the north coast, they're kind of around the corner from us. And we would be more closer to the Isle of Scilly, and Scotland would be. On a clear day we can see the mountains of the Scotland. And this night we looked, it was around 7 o'clock, seen the aurora, it was coming up, substorm in progress, next minute, yellow alert, orange alert, and I was like, oh, there's something really interesting going on here. Only because we spoke to the guy, Adrian, he said, when you get the orange alert, go. If you clear skies, head to a dark spot, go. So we did that. When we arrived in the mountain, I did a test check of the camera. Luckily, sometimes when we are up on the north coast, my mobile would go on to O2 Ireland. So I have to,
Right,
the signal would go, done a test shot, seen the green, the low green, and the arc started growing. And I thought, wow, this is, and now most, usually about 7, 8 times out of 10, if anybody that follows us on the social media, you'll see, we always battle clouds, but we go out anyway. And that night was perfectly clear, and the next minute I checked the stats again. An interplanetary shock happened. This just came out of nowhere, and the next minute we went on up a bit to the mountain, and I mean you could see the pillars at this stage. Now with naked eye, because there's still quite a bit of light pollution, the lower, we're about 520 feet above sea level where we are in the mountain. But we could see the pillars kicking off, and it was the best display I've seen in a very long time. But learning, people how to follow, these stats on these apps that you get. A lot of people were going by the KP level. If that's high, that means aurora, but that doesn't necessarily mean you're going to have a really strong, aurora or see it. There's so many components to the aurora. Just break it down kind of so people really understand. You have an interplanetary magnetic field which must be aligned with Earth. I can share the link of the app that we follow, but the aurora, it's broken down. There's a chance of the aurora. You'll see in the app there's growth happening. So if everything's aligned, the aurora will be on a growth period. Then you'll see substorm. So what substorm means, you think of like a battery. So when you're charging your phone or like a car battery, you're charging the energy so that it's full. Then it goes into the expansion stage. So the expansion means that energy is full, it has to go. So the expansion then, it turns into the aurora. And then for a period of time, you get the chance, dependent on the solar wind speed and the conditions, the INF, your BZ, that's another thing as well, if you go north or south. If you're more south, more northerly, and the perfect conditions, clear skies, you have a chance to see it, like us here, if you're more in the south, vice versa. But if there's a big enough interplanetary shock, everybody will get it. But that night, we got the aurora. We only found out we actually see the International Space Station went over that night above us. But because we had the camera set up, it was quite higher up in the mountain, it's a bit windy, and then you're focusing. We didn't want to touch the camera. 2 days later, NASA astronaut Shane Kimbrough posted that he took a photograph as this International Space Station was going over the UK and Ireland. So at the same time, when we got this amazing, after this interplanetary shock, he took a photo as well. So we shared the photo on Twitter, and then the US, the Irish Embassy of the USA, they picked up on it. So Shane Kimbrough, he shared the picture from space. We got a like. So there you go.
Oh, that's absolutely wonderful.
But we are still learning, so much. You look at these graphs and all these wiggly lines, and people are like, what is all this? But, the basics, clear skies, you look at INF, and then with the thing, growth, substorm, expansion, recovery, and if the BZ is going to be north, south, and depending on the CME as well, how strong it is, and the solar wind speed. That's my simple form of breaking it down.
That's very well explained, Caroline, because a lot of people get mixed up with the KP and the BZ and the everything, you know. So you've explained it very well there. Can you tell us about, though, when people go along to look at Aurora and you're all there waiting and you've been waiting for an hour or half an hour with nice dark eyes, dark accustomed eyes, and the next thing somebody comes along with the car headlights or torches or turns on their phone, what happens?
Oh,
Yeah.
that is one of my pet hates. You know, you see a lot of media reports, you know, they put out chance tonight to see this aurora, and you know they put up all the naked eye you're going to see, but people don't realise we're in Ireland or UK or wherever you are. We're not Iceland or Norway. We're not going to see this dazzling bright show the what you get over there with naked eye. But in the night sky, you know, with the photographers especially, get people coming out to try and see the aurora. They're not going to see it with naked eye, especially if it's cloudy, dark night. And you know, there's somebody in the media, or tonight you're going to see it. But we've had this before. You know, we've tried to, you know, not patronise people, but try and be friendly. You know, and set up the camera and let them show them. But whenever you get your eyes accustomed, not just the aurora, but night, you know, if you're out looking at the Milky Way or nights in a meteor star, but when you have car headlights on, you know, your eyes just dreary. It becomes dreary. It's so hard to get the focus back. You know, people are excited, and you know, you have to give leeway when people is out as well, setting up, you know, their cameras, and you know, they'll need a torch on, but we have learned as well now to use, there's like an infrared kind of torch to get, so it's not as harsh. You know, if somebody is already set up, so then you have the infrared, so it's not going to startle somebody that they're going to lose, you know, that night vision that they have, you know, got themselves accustomed to.
How long does it take your night vision to come into focus on average?
Well, if you're out, say, like at the moment, I'm sitting here in my kitchen. Well, we don't have clear skies tonight, but if I went outside, it would take me, you know, you look up the sky, fix your eyes, and it would take maybe 5 minutes to adjust.
Yeah.
But, see, I've got into the habit now, I have my phone in my pocket, usually checking stats where I left my phone, because if the phone pinged, look at your phone, but then when you look back up the sky, all you can see when you blink is this square bright box. You know, it's
Yeah.
you know.
So what would you recommend, about a half an hour, like, to really get your eyes ready to you know, see details, not just the main stars?
So get yourself out and get yourself set up, you know, comfy. If you have a camera set up or a telescope, you know, make sure that everything's set up, and just give yourself time before you even start twiddling about with the camera. You're setting stuff. Just give yourself time. Look up at the sky. We would always try and do, you know, like 20 minutes, and it all depends as well on your eyesight as well. You know, you're different. You know, everybody's different. But always give us time.
Okay. And just to say that Caroline and her son Hayden have an amazing article that's coming up in our December issue of Astronomy Ireland magazine. This is the interview they did with this chap Adrian. I can't pronounce his name.
Adrian Madui.
Madui, is it?
It's Madui.
Maybe. I have to look at his name again.
It's French. He's such a lovely guy. Like, you know, we're so blessed, you know, people that, you know, we've got to talk to. And the aurora was always something that, you know, Hayden and I wanted to get a feature on. And the amount of information and photographs that we get us access to, it's, you know, it's like a Christmas present come early.
treasure trove. I know all the extra information you can look at now.
It's fantastic, and he explained it very well. It's great, and the questions were great. The whole thing, it's really good. Yeah, I'm sure everyone will really enjoy reading it now.
Yeah, well, we're not going to give any spoilers away, but there's one lovely surprise picture, and it's going to fit perfectly for all the kids, the kids' families, readers of the magazine. So, no more spoilers, but
It's true. It's beautiful.
special.
We're zipped up. But and Caroline, I don't know if we have any more about the Aurora, but you also have a huge interest, both you and Hayden, in the Hera and Dart, particularly the Hera, but the Dart and Hera missions.
Yeah, that mission, there's a big story behind it. You know, we are talking about it whenever we see live stuff and the progress. It's quite an emotional attachment for me, because Hayden is their youngest planetary defence ambassador. But we've been involved with Hera now for almost 4 years. Part of the planning for that mission, before they actually got the funding for the European, the ministerial, we were over at one of their planning, it was the phase B1 workshop, when everything was getting, put in place ready for going for this funding. So we were invited to Madrid for that. And to be in the room with the full team, I've never met more amazing people in our lives. And it was a big shock and surprise that they awarded Hayden that day when we were in Madrid. I could talk about it for hours, but
Yeah.
but with the Dart mission, that is launching now next week. So Dart, that's part one of this mission. So it's a joint mission with NASA and the European Space Agency. So there's NASA's, it will be first time for this mission going to a double asteroid redirection test. So the launch window opens 1:20 a.m. Eastern Standard Time, November 24th, and that'll be launching from Vandenberg Space Force Base on a SpaceX Vulcan 9. So I'm wondering, it's launching from there, will we get to see the rocket separation like we did with the previous, it was a ULA launch a few months ago. So I don't know, but the time, maybe we might get to see something in the Irish and UK skies. So the whole purpose of this mission, they're going to test out the planetary defence, kinetic impactor, redirection test. So whatever case may be, if Earth is going to be at risk from an asteroid colliding with us, that we can do something about it. With this mission, they can test, see if this is going to work. So Dimorphos, which is the new name given to this asteroid, it was discovered in 2003. Originally, they were given the names Didymos A and Didymos B. So little b was the moonlet of this asteroid. So they're Apollo-type asteroids, S-type synchronous asteroids. So whenever DART launches now next week, it'll be late September in 2022 when they arrive to this asteroid system. So what is the purpose? They're going to crash into this asteroid. Sounds very Hollywood. People think crash into an asteroid. First thing a lot of people think of is Bruce Willis.
Yeah, Armageddon.
Armageddon. But it's not going to be quite as dramatic. It is exciting because the spacecraft that has taken years to build, they're going to completely crash this into this asteroid, Dimorphos. So all they want to do is make a crater and change the trajectory of this asteroid slightly. So it's just going to be like millimeters. It's not going to be a major change. So that is not the part of the thing. You're not just going to crash this and that's it. There's a camera on board, Draco on board the DART. Like previously with the Hera mission coming in, originally in 2016, the Hera mission was a different mission name. It was called AIM. Whenever they went to the ministerial to get funding, it didn't get funded. So what happened, the Hera, which it's known as now, would have been launching and following DART a lot sooner. So why the big gap? So in 2019, they got funded. And so the DART launching next week, be arriving late 2022, and then the follow-up in 2024 is the launch of Hera. Because with the trajectory, it's going to take 2 years for its journey to get. So they're going to follow up the impact, what DART has done. They're going to map it. They're going to science it. And to see what this asteroid is made up of and the outcome of the impact of its work. But in the meantime, there's not a big gap. You have NASA and the European Space Agency. We have a European element that's going to be traveling with the DART spacecraft. So it's a company called Argotec for the Italian Space Agency. So on board of DART, there's a little mini satellite called Lucie Green. So that is going to be deployed 10 days prior to DART hitting this asteroid. And Lucie, the imagery on this mini satellite is going to get all the action prior, during, and after. Also the ground-based telescopes, amateur astronomers, anybody involved with real serious imaging will be able to image as well from the ground. So it's very exciting, for everybody around the world. So.
And Caroline, even though it's only a very, very slight adjustment to the trajectory, if that was one coming towards Earth, I know this one isn't, but if it was one coming towards Earth, that would be enough if this works to deflect it away. That's the plan, isn't it?
Well, currently, with the binary asteroid system, now the orbit, with the moonlet, it takes one orbit 11.9 hours. So with this, the impact, it's only going to slightly change it about 10 minutes. So it's not a major, but it will be enough. In the event, we're not at risk from this asteroid, but in the event of, we're not at risk from any asteroids for 100 years or more, but it's still with so many not discovered. But in the event, with new technology and the telescopes and the ESA fly-eye, different missions coming up. If there was one discovered, and then, they work out the trajectory, if they have so many years in advance to find, if this does work, then this will make a major, huge difference to us here on Earth.
It's a really good starting point to build from, really.
Yeah.
For if we ever do come down to that in 100 years or so.
Well, what I was going to say on that subject is the fact that we had an unexpected visitor. It was the Jablinsk airburster. Nobody was looking in the direction it came from anyway. And then it came in, it entered the atmosphere, and it blew up in the air, doing the damage it did. So the big problem is we can't look everywhere at once. Now, due to the fact that there were so many webcams and dash cams that recorded it, a lot of the astronomers were able to backtrack where it came from. So they now added that area of the sky to the list to be monitored.
Yeah.
But in a lot of cases, the biggest wake-up call we ever had was Shoemaker-Levy 9, because the whole world watched it impact into the Jovian atmosphere. And it was, as most, well, as I say, Neil's going to say, yeah, Nick's talking about his favourite comet again. Yes, I am. But the thing was, there were crater chains on Callisto that we couldn't understand. They were crater chains that were marching in a straight line, one after the other. And until Shoemaker-Levy 9, and when we actually got to see how it had impacted on the Jovian atmosphere, we didn't understand how those craters could have been created through the normal bombardment method. In fact, there is a series of crater chains on the Moon, and there are some here on Earth. Most of them are pretty much well eroded away now. We've only got the ghostly remains. But it took something like Shoemaker-Levy 9 to really make the world sit up and listen to the few scientists who had already been banging on about it, that somewhere out there is a piece of rock or ice with our planet's name on it, and it will be Chicxulub all over again.
You know, there's a lot of the asteroid missions, Comet, ESA's the Comet Interceptor coming up now in 2029, due for launch. A lot of people say, why planetary defense? Or, but why not? Because there's so much we have to discover where we evolved from. Like I'm sitting here, Asteroid Day, Danica Remy always says in her talks, I'm sitting here with a glass of water. Without that asteroid hitting Earth, I'm sitting here with a glass of water. And that always resonates with me. With planetary defense, it's a big deal. And again, media, hype it up, there's a big giant thing the size of a football field that's going to hit Earth, and dramatise the thing instead of focusing on more about actual learning, the importance of it. But that's something that me and Hayden is working on to change, along with a bigger community as well.
And I think that practically every day an asteroid goes past us, doesn't it? Barely noticed, unless one of those red top newspapers gets hold of it, and then suddenly... it's the Armageddon 1, 2, 3, 4, 5, 6, 7. What episode are we on now?
Well, I was more thinking the Sean Connery film Meteor.
Yeah.
Because they actually used nuclear weapons to deflect the meteor, not to destroy it, but to deflect it. So they used the bow shock from the actual explosions in space to change the orbit of the meteor and protect the rest of the world, even though some of the shards from that meteor are already impacted and caused devastation. The idea was using a missile system pointing outwards, which, to be honest, right now is highly illegal due to the Outer Space Test Ban Treaty. I think it was 1963 or something. And also, it then also demilitarized space as far as nuclear weapons was concerned. So we can't do something like that movie suggested.
The thing is, as well, with this double asteroid system, Dimorphos Didymos, the teams have modelled, they have a fair idea of what this asteroid is made up of, but until we actually get there, they've imaged it. It's different seeing the white dot going across the screen. But until they actually get there, it's the same with the Ryugu, not Ryugu, Orion Rec mission.
Yes.
That the touchdown to grab the sample. But apparently the way that asteroid, the double pi, if they had to got away quick enough, I know they got in time to get away, in, out, touch, grab, go. But that craft would have went a lot further.
Mm.
You know, but it's until they actually really get up close. You know, and that's the exciting part as well. Discovering what it really, really is up close.
Yeah, and when DART arrives there, like, how long will it be before we get information back that we can actually see or understand? It makes us
Well, DART, they have it's an imagery called Draco on board. So when they get there, you know, they're not just going to go bang straight into those asteroids. They're going to
Yeah.
get first. And then 10 days prior to the
Oh,
impact,
yeah.
we have the Italian Lucia cube, which will be orbiting that moon, the moonlet, and so that then when they're ready to go for it, they will get prior. So the ejector, you know, the impact, that's going to get hopefully everything, and then the exciting part as well. You know, the citizen scientists and the amateur and the more advanced, you know, astronomers, ground-based, you know, to get that as well. So it's exciting. And of course, we're going to say that.
Well, the interesting thing is, if we look at the Martian moons, I think it was Phobos. There's a good chance it's actually it's a captured piece of space rock, and B, it may actually be a rubble pile that's only being held together by gravity. That's the interesting thing about a lot of these items, which we call asteroids. Some of them are purely rubble piles with the only thing that keeps them together is their own gravity.
Well, recently, Patrick Michel and Brian May, they did like a stereo, you know, on the Dimorphos, Didymos, and the way they described it, you know, if you look under your bed, you see, you know, those dust balls. That was like a description of, you know, I must hoover under my bed. I think I've got dust balls under there, so.
And of course, one of them is due eventually to impact on Mars anyway. It's slowly creeping in, and once it reaches the Roche limit, it will completely disintegrate, and then there'll just be a shrapnel effect onto the Martian surface.
But will be exciting. So after the impact, because on board then the Hera craft, we've got two CubeSats, Juventus and Milani, the spectrometer imaging on one of those cubes. It's actually the same that was on the Rygu mission, JAXA. It's actually going to be the same instrument on this, so they're going to get a lot more
Hayabusa
detail. Yeah.
Yeah.
So it's exciting and a lot to learn, and it's going to keep us all busy for a few years.
Absolutely.
In fact, my memory goes back to a BAA Comet section meeting held at the Open University. This was quite a while ago. I think it's when I first met the likes of Richard Miles, etc. Dr. Simon Green was talking about OSIRIS-REx and the fact that it was beginning to be believed that a lot of the asteroids themselves were rubble piles, and he gave a very fascinating lecture about why they were thinking that and how it would actually happen and what conditions were required for it to maintain stability to be seen as a side object by us.
So they're very loosely held together just by gravity, is that it?
Well, pretty much, yes. Basically, it seems like the gravitational attraction is what keeps it together, and there's nothing really solid there. It could be very easily disrupted by an impact, say another piece of space rock moving at maybe 3 or 4 miles a second hits it, and that could shatter it, and you'll just have more and more smaller bits.
Well, I'm looking forward to all the imaging and the science and the mapping. It's going to be very exciting to actually get a definite, especially with this one, the Didymos and the Morphos, to actually see, to get more sort of concrete evidence of what they are, and it's very exciting.
Oh, it
And
definitely
hopefully we
is.
get to see the separation stage over us. Next week it is, isn't it?
I'm hoping, because
Next
I'm
week.
hoping by I could be completely wrong. Somebody correct me. The time it was, I think it was the ULA launch that launched from there. We could remember everybody seeing this big bright thing in the sky.
Yeah.
That's what it was. But
Because usually the last place that they check in for anything is with Shannon, and the south west of Ireland. That's the last sort of station. And you often hear them. You just hear Shannon being mentioned very quickly. Sort of over the. So yeah, maybe we'll be lucky. I'll try and find out more about that between now and.
I suppose it'll all depend as well if the launch time. I know they have quite a big launch window.
Yeah, it
So
might
it'll
go
all
different.
depend. It all depends. So hopefully we might get something exciting in the skies.
Yeah, it would be really nice to see it going off, and then later on to follow up what's happening as the years go on.
Yeah.
Yes.
But Hayden will be 14 years old. We're actually going to the French Guiana for the Hera mission launch in 2024.
Fantastic.
So Hayden will be
Wow.
14 years old.
He'll be 14 then. Wow.
And
Wow.
so
Yeah.
whenever they start the progress for the Hera craft, we're taking them over to Bremen to see that before it's taken away.
Fantastic. So he'll be able to more or less see it through its various stages along the way. Oh, that's great. It's
It's
fantastic.
really lovely to have that to look forward to as well.
Yeah.
Yeah.
I'd say he'd be buzzing, literally.
It, he's taking everything in his stride, the Hayden loves talking to people.
Yeah.
Doing these things over, you can't see people. He finds it difficult. But you see when he meets people face to face, Anne will tell you, hugs galore.
Oh, I tell you what, he'll be over with hugs.
Well, what I suggest then, Caroline, is that when you and Hayden go over for the launch, take a voice recorder, and he
Yeah.
can become our special correspondent from Coronal.
Yeah, definitely.
Yeah.
Yeah.
Yes.
He's coming on a long way doing these things, so yeah, he would definitely be your number one reporter.
Yeah, I like the sound of that. So there was something else then. The big story this week was the Russian satellite, and poor Susan has her pet, I don't mean poor Susan. Her pet topic is space debris, and we lost a recording recently about it. So on top of all the existing space debris, we now have this major disaster.
Yeah.
And
Actually, what happened, I couldn't actually believe it. When I read it, I read it late at night and kind of thought maybe it wasn't real. The poor astronauts, some of them only got there on the 11th. This all happened to them then a couple of days later. And it's to do with the Russians taking down one of their satellites, but they took it down with a missile. And nobody really from what I could find out, really seemed to know that they were going to do that until they came into the field of the debris, which was pretty horrific for them. They had to get into the Soyuz capsule, and obviously NASA had to do a huge amount of calculations and work, because it was every 90 minutes for the first evening, but space debris in general. Huh?
Like the film Geraghty, is that the one where the pieces are coming around, Yeah.
It's literally just, this is when I read it, I didn't actually believe it for a moment, because it's just that's what happened in the movie.
Yeah.
But it's incredibly scary, and I said some of them only up there, I think they were there 2 days, and it was their first proper working day in the station, and they had to go and hide themselves in the Soyuz just for protection. But 1,500 pieces of space debris that they're now tracking just from this. Now they're now tracking, but I mean, there's so much more. There's hundreds of thousands of smaller pieces that they're not tracking or they can't track. And that's on top of let me get this right, I have it written down, the amount, it's 120 million tons up there, at the moment. And there's around 20,000 pieces are known and they're tracked daily. But there's so much more, and it's just getting worse and worse. And it's just getting out of hand. Like, they come up with some small ways to, they have a laser broom to try and help. They have nets. They've harpoons. They have a claw going up in 2025. But none of these things are actually going to make it less. They might just stop it getting much worse. But it's, to me, it's just terrible. I mean, somebody, thank God nobody was hurt, but somebody could have died. And I think, unfortunately, until maybe an astronaut is hurt, people won't really take it seriously. And it's always somebody else's problem. So, that's scary. And then it is. So it's absolutely out of hand. I mean, at the moment, there's, like they said, there's a glove, there's a camera, there's a blanket, there's a wrench. There's somebody's toothbrush. These would just be stuff they're lost on missions, like just flying around up there. With people, and then there's plenty of other stuff that get lost on missions. And then, of course, there's satellites. Then there's just going to be stuff that happens to things up there that they get damaged, and that creates more debris. And then the debris smashes into each other, and that creates more debris. And then you're going down the Kessler effect, the Kessler syndrome, which they were talking to us about back in 1978.
There's also a toilet.
But I'm really hoping.
What, a toilet?
Yes, a toilet from the ISS.
Yeah, there's crazy stuff like floating around up there. Apart from the obvious stuff, I mean, I'm kind of fascinated about the toothbrush. Like,
get out there.
Like, what's they bring it out for? Like, it's not like they're going to be brushing their teeth through their helmets. It's just pretty. But it's a very, very scary thing, and I really do feel. I felt very sorry for reading about the astronauts and them having to, emergency kind of into the Soyuz, and the 4 new ones, and there was 2 up there since April, and I know there was another one joined in September. But I couldn't even imagine you'd have no protection. You're just doing what NASA has given you an idea of what to do, and unfortunately I think this is going to happen again, and it's going to be worse. And somebody's going to get hurt, You
think that it was just a fleck of paint hit the cupola and put a little dent, took a little chip out of it, and that was only a fleck of paint. So if you imagine it like a wrench or whatever, or all these pieces of this Russian satellite.
They're going around 15,000 miles per hour, like each one. So the tiniest thing it's completely different up there. It's a missile in itself. And I just hope people that are listening, people that it made the news, that maybe normal people who maybe wouldn't have any interest in space or any of the above, realise that space debris is a big problem, and it's a dangerous problem, and it's an ongoing worsening problem. Yeah. But anyway, rant over.
Well, the thing is though, a lot of new satellites.
Sorry, Nick.
Sorry, okay. As I say, a lot of new satellites have to provide a method to deorbit them once they've fulfilled their lifetime. So they are making efforts, but there's Centaur stages up there. There's Apollo, Saturn 5 and Saturn 1B stages and everything up there still.
And what's with that? Mentioning the M word. What about all the Starlinks? Are they going to do when time comes?
Our own atmosphere is great at helping get the satellites sent if they're in a low or orbit already, but still that takes time. Now I'm not sure what exactly Elon has put into each and every one of them, but I'm sure he'd had to have come up with something. But I mean, they're all still in working order at the moment, but they won't be forever.
Like
the Starlinks.
The European Space Agency, they had emergency. I think one of the missions, the Earth observation missions, there was one of the Starlinks was nearly in collision. One of the Earth observation spacecrafts, and then recently, due to debris, they had to do a whole, change the orbit to get into safety. So those people are working around the clock, and that, they get so much notice and they have to take action, and, and then with this fiasco, it's, with this cloud, time will tell what.
Well, if you think about it, this latest incident stems back to when the Americans, with United Nations approval, destroyed one of their malfunctioning spy sats that was re-entering the atmosphere with a full fuel tank of hydrazine. Now, hydrazine as a propellant is highly toxic and carcinogenic. So what they did was they used, I think they used a Super Hornet linked to 2 Aegis destroyers to do a vertical climb and fire an anti-satellite missile to destroy the satellite as it was re-entering. The plan was to rupture the fuel tank and ignite the hydrazine, so that anything that actually got through to the surface would not pose a threat in regards to the actual hydrazine itself, because they weren't sure whether the tank would implode during re-entry, or if it was going to survive all the way, crash land and then split, contaminating either the sea or the ground with the fuel. So the Americans actually successfully ruptured the tank during re-entry, so the fuel burnt off. It apparently was quite a spectacular sight. So this is, from what I understand, Russia's response to an event that was about, I think, 3 or 4 years ago now. Because now they're saying, yes, we can do it too. Not just the Americans, we can do it. Of course, the Chinese have been quiet. Having said that, they're up to their state-of-the-art space station, being where it is now at risk from this debris field. Nobody knows if they have the ability to move the station to a higher orbit like the ISS can do. So, as I say, it's just a waiting game to see if the movie Gravity becomes real life.
That's
the reality, yeah.
They're not going to have as much access, to the international space stations that they have with ground. Kind of the Chinese space station is independent. They're not going to have the same, what's going on. As much comms and, so it's worrying for every nation. But just crazy and madness, what happened the other day, it's just
hard to believe.
Well, to the best of my knowledge, China hasn't attempted this themselves. But I could be wrong. Someone may correct me in the comments. But as I say, it's really, really crazy polluting low Earth orbit so badly. Because in the end, it's not just everybody else's satellites that are going to get hit, it's your own too. So this debris could actually take out Russian communication satellites just as easily as take out European or American or anybody else's.
And then the launches of future missions. I mean, how are you going to send something up through just debris,
Well, as I say, some of it eventually might deorbit. It really depends. The good thing is, if we get a really, really good solar storm, maybe an X5 or X6 solar flare, it causes the Earth's atmosphere to expand, which is part of the danger to satellites from solar weather. So that will pick up, that will catch the debris and start pulling it into a re-entry.
And then also as well for, there's a planned spacewalk, I think, due in a couple of weeks. So that's going to have to be taken into consideration, and a whole new kind of risk calculation on that as well.
Well, Caroline, you're setting a record because we're now 1 hour and 20 minutes almost. And on your first show.
Yeah, well done.
Wow.
Well done. Just going back to the Aurora, can I just mention a really good book that it's nice and small. It's not a big tome or anything, and it's just tells you everything about auroras, their history, the myths surrounding it, how it was recorded in in antiquity, and then how they form, and how to photograph it. And it's called Northern Lights: The Definitive Guide to Auroras by Tom Curse, and it's in conjunction with the Royal Observatory Greenwich, published by Collins. I'm sure Nick will put that in the notes afterwards.
Yeah.
That would make a good, great Christmas present for people that is interested. Good, great stocking fillers. So that's a brilliant recommendation.
Yeah, absolutely. Now, so we haven't recommended in our oh no, we haven't actually, but we'll get to it. We'll do a review on it soon. So it's been really nice, Caroline. It's lovely, and you explained everything so well. And we've lost Susan.
Oh.
Yeah, she dropped.
Oh dear.
Oh dear. But she got her ranting, so that's the main thing.
Well done, Susan.
I think it's... As I say,
really
I think...
appreciate you having me on, and
Oh, we'd love to have you back.
Yes.
Hayden, he would have loved to have joined. We put a thing up on Twitter that we were joining tonight. So some European space agency people seen it. The CA Cube account shared my tweet, and I says I would put the link up whenever it's available. So I'll just have to explain that. But they're saying, why is Mummy talking? A lot of people understand, with Hayden. Unless if he's face to face, he could talk the legs of a table.
Yeah.
Well, what I'm going to suggest, Asteroid Day will be coming around again next July time.
Yeah. June.
I think we should have a Comet Watch meets Anglo-Irish Astro Geeks show for Asteroid Day.
That would be amazing. Then you can get the Astronomy Day site and get it promoted and reached out as well.
And maybe Hayden might be able to come on and have a little chat with us.
Yeah, definitely. But he kept me busy all day. He has given me, I'm sitting on my kitchen table with about 20 cue cards. So all the information is thanks to Hayden today.
Well done.
Can I just wish Hayden a happy birthday? I know it's a little early, but it's in a couple of weeks' time. Hayden will be 12, and he's still our youngest ever correspondent in Astronomy Ireland magazine.
Yeah. First, we are going to the Waterfront Hall in Belfast, and Tim Peake is coming on that date, his birthday. Oh,
fantastic! What an amazing birthday for him.
So in Hayden's head, if I share it on Twitter, if you're listening, Tim, Hayden believes you picked that date for him, so we'll go with that.
Well done, Tim Peake.
Well, I think we're coming up to 1 hour 24 minutes, so I think this is probably a very good point to actually wrap the show. We probably could go on for ages. Neil and I have done that before, haven't we, Neil?
We have, yeah. About 2 hours, I think, something like that.
Nearly 3 actually on one show.
Nearly 3.
Me, I took a lot of time talking about Dart and Hera and the CA Cube, and the launch is next week, so we have to...
No, it's very exciting, Caroline. Thanks a million. It's really interesting.
Natural. You're a natural.
Yeah.
So.
I think I went to another show.
So I'm going to say, on that bombshell, I think it's actually time to say good night. So it's good night from me.
Good night from us.
Arrivederci from somewhere in England again.
Sayonara.
Slán from Ireland.
Good night from here from us on the cloudy north coast.
And last month we interviewed the wonderful Professor Lucie Green. Unfortunately, we lost the second part of our recording due to Skype and internet issues. Please enjoy. Thank you.
Hello and welcome. And would our guest tonight like to introduce herself, please?
Yes, I'm Lucie Green, and I'm a solar physicist / space scientist working at UCL's Mullard Space Science Laboratory.
Well, with us tonight we've got Anne, Neil and Susan. Anne and Susan are in Ireland, and Neil and I are here in the UK. So let's get going. So, ladies first.
Go ahead, Anne.
Oh, hi Lucy, it's really nice to speak to you.
Hi, it's good to be here.
Hi, I'm Susan. Lovely to meet you. Delighted to meet you.
So I don't know where, I was just looking up, I had one question, but maybe it's not the first question to ask you, which was about the Parker Solar and Solar Orbiter. What's the difference between the two of those, and are they collaborating? Because I know one is sort of looking at the sun and one is looking away from the sun, but are they joining their data up?
They are. So they are highly, highly complementary missions. So Parker Solar Probe is NASA's mission to get close to the sun, and Solar Orbiter is Europe's mission to get close to the sun. But they are doing slightly different things, and actually in very different places with respect to sort of how far they are from the sun. So Parker Solar Probe goes much closer in and will get to a distance of around 10 times the sun's radius. So that's really, really close. And because that spacecraft gets so close, it puts it in a really perfect position to get sort of into the atmosphere of the sun. But because it gets so close, it heats up to, I think it's over 1,000 degrees Celsius on the sun-facing side. So that means it's very difficult for that spacecraft to carry on board telescopes that look at the sun. So Parker Solar Probe is really designed to sense and sniff and taste the solar atmosphere around the spacecraft. It doesn't look at the sun itself. Whereas Solar Orbiter, which gets to just over a quarter of the Sun-Earth distance, so it's about 7 or 8 times further out than Parker Solar Probe is, at that distance, even though the spacecraft on the sun-facing side heats up to around 500 degrees Celsius, it's still able to have telescopes peek through a heat shield and take images of the sun. And it also sort of sniffs and senses and tastes the atmosphere at that distance from the sun around the spacecraft. So you've got this kind of mini string of pearls with Parker Solar Probe and Solar Orbiter, and then instrumentation further out that sort of allow us to study the sun from close in, but at these two different distances.
Oh, very good. And one other thing in relation to that, Bepi Colombo, is that going to do any kind of sun science, or is it strictly Mercury?
Well, Bepi Colombo, you're right. So Bepi Colombo is a mission to study the planet Mercury, but at that distance, I mean, it's still sort of the same, similar distance to the sun as Solar Orbiter gets at its closest approach. And in fact, there's sort of common aspects of the technology that were developed for Bepi Colombo that are then being used by Solar Orbiter, because they're both they're both ESA missions. So Bepi Colombo, in its measurements, in its in situ measurements at Mercury, so again the sniffing and sensing of the particles and magnetic fields around the spacecraft, those data sets will also be important for studies of the sun as well, because the planet Mercury is immersed in the atmosphere of the sun, in this solar wind streaming out from the sun. So when we visualize the sun, I visualize it as having a very extended atmosphere, and that all the planets sit inside that atmosphere. So in fact, any kind of measurements throughout the solar system can be used to ultimately study the impact that the sun has on these other bodies.
Great answer. Thank you. That's really good.
Amazing.
Yeah.
So theoretically, the solar atmosphere, as you were describing it, could actually extend as far as the heliopause?
Yes, yeah, exactly that. So the atmosphere of the sun is it's very hot, it conducts heat very well, and so sort of pushes itself outwards, and in fact the sun's gravity is not able to hold on to the atmosphere once you get to a certain height. So the atmosphere puffs out and in fact is sort of dynamically expanding out into the solar system, and it creates this bubble in space, and the edge of that bubble is the heliopause. So that encompasses all the planets, the asteroids in the asteroid belt, and goes out to, well, I forget now exactly the distance, tens of billions of kilometers from the sun. It's not a static bubble, so it kind of expands and contracts depending on solar activity, because the sun has this cycle where it waxes and wanes in complexity and activity over about 11 years, and the size of the heliosphere responds to that. And I think that's been one of the really great discoveries of the space age, is that even though there's not much material out there between the planets, there still is some, and it originates in the atmosphere of the sun, and it creates this big bubble in space called the heliosphere. And the two Voyager spacecraft over the last sort of decade now have become the first two spacecraft to leave the heliosphere, and they crossed into the interstellar medium. So we finally have a couple of data points as to what the conditions are like at the edge of the heliosphere. So in my mind, I define the solar system by where the heliosphere ends. Some people will be thinking, oh well, the solar system maybe ends where the Kuiper belt objects end, but in my mind, because I study the sun and I'm fascinated by the sun, I sort of define it by the sun's physical extent.
Would you think that the where the heliosphere is, just like where Voyagers have been in the last while, would it be a bit sort of like waves crashing onto a shore, that it must be a bit of a grapple going on between the interstellar area, and the final bits of the sun's influence?
Yeah, that's right. So the heliosphere, the atmosphere of the sun, is expanding into the stuff between the stars, the interstellar medium. And you're right, there is this kind of battle, this sort of the pressure of the heliosphere pushing out, and the pressure of the interstellar medium pushing back on it. And so that's why the heliopause, so the edge of the heliosphere, isn't fixed in space or fixed in distance from the sun, because it depends how strongly the atmosphere of the sun is blowing out, and whether it can sufficiently push against the interstellar medium, or whether the interstellar medium actually is able to sort of push back in sufficiently to squash the heliopause in.
So that's the far extent. Sorry, I'm hogging all the questions here. Somebody else can go ahead.
Okay. Now, I know that your area of interest is the evolution of the sun's magnetic field and how it drives solar activity and space weather. I'm going to put on a different hat from an astronomer. I'm going to put on my radio amateur's hat. Could you perhaps explain that bit more? Because a lot of my radio amateur friends will be actually listening to this podcast.
Yeah, so I really like the fact that there are these different communities that are interested in sun's activity. So for me, I'm interested in how the sun operates as a star. And one of the aspects of the sun that's been known for a few hundred years now is that the sun is an active star. So it produces these dark spots on the surface that we call sunspots. I'm sure listeners will have heard of sunspots, and the number of sunspots varies over time. So we go from a phase where there are very few, perhaps none at all, then the number ramps up, and then it drops off again over about an 11-year cycle. But going hand in hand with that increasing and decreasing number of sunspots is an increase and decrease in what we call solar activity. And by that, we mean explosions and eruptions that take place in the atmosphere of the sun. So solar flares are these explosions where you have sort of sudden, very dramatic events in the atmosphere of the sun, where you have the gas heated up to very, very high temperatures, and large amounts of light produced across different wavelengths. So it could be ultraviolet light, it could be X-rays, extreme ultraviolet. And then we have these eruptions from the sun's atmosphere that we call coronal mass ejections. And I sort of visualize those, well, they are these big bubbles of gas that get detached from the sun and head out into the solar system. Now, we are living in the proximity of this active star, and when the activity events happen, they can send electrically charged particles towards the Earth, light of very short wavelengths or high energy towards the Earth, and bubbles of magnetized plasma towards the Earth. And what can happen is energy that's absorbed by the Earth's atmosphere. So there's like a whole chain of things I'm kind of cutting short here. But if we just think about the atmosphere above our heads, energy that's absorbed by the Earth's atmosphere can change the Earth's atmosphere in ways that impact the propagation of radio waves around the Earth. So, I mean, you'll know in way more detail than me about the bouncing of radio waves off of the Earth's atmosphere, so you can see over the visible horizon. And when you change the details of the Earth's atmosphere during solar activity events, then what can happen is, rather than your radio waves being reflected off certain layers of the atmosphere and propagating around the world, they might pass straight through. And so you would lose then your connection. And that happens more often at times of solar activity. So yeah, it's not just people like me who are interested in the activity of the sun. It's radio operators, ham radio operators, or it might be I don't know, all kinds of industries organizations that are needing to communicate via radio waves that then might lose that ability during times of heightened activity.
Great, thanks. I know another thing a lot of people will be interested in is all the various different classes of solar flares. Most people have heard about X-class flares and how they can affect not just seeing aurora, but how they can affect the power grid and everything.
Yeah, that's right. So the sun produces very, very large flares that we call X-class flares. So we love to categorize. And depending on the amount of X-ray radiation that we receive here on the Earth, we will then categorize the flares. And there are some American satellites that receive that radio, those radio waves, and allow us to measure how high that flux is, how much X-ray radiation are we receiving. And typically we have this scale that goes A, B, C, M, X. So A being the smallest flares with the smallest amount of X-ray radiation, and X being the largest. But actually, the more we look at the sun, the more we realise that spectrum actually extends on both ends. So we have had a small number of events that have produced very, very high energy X-ray flares that have kind of gone off of our detection spectrum. And then at the smaller energy end, we have lots and lots and lots of very small energy flares. So it's, I think it's kind of about what we can detect, what our detectors are designed to detect. But actually there's a whole spectrum where you've got lots of lower energy little flares going off all the time. And then you've got a much smaller number of very high energy events that, because they're so infrequent, we haven't necessarily designed our detectors to be able to extend up to that high energy range, because we didn't necessarily expect that the sun could produce that level of radiation. But what's interesting is when you look at other stars that are like our sun, and then you can look at a large number of stars, and some of them do produce flares. Well, many of them produce flares. That's a kind of standard of stellar activity. But there are many stars that produce very energetic flares, which actually is a kind of indication that if you look over a large enough sample, or conversely, if you looked at our sun for a long enough time, you would see these rare but very high energy events.
Yes, I have to admit, one thing I do love about our sun is the fact it is a variable star in its own right. I seem to remember it was classified as a G3 dwarf, but variable.
Yeah, that's right. And the sun has, and other stars in general have, this really important aspect to them, which is a magnetic field. And we're all familiar with the Earth having a magnetic field. Stars have magnetic fields too. And for our sun, the first time that was detected was in 1908. So we've had, just over 100 years now of studying the magnetic side of our sun, and other stars' magnetic fields are now being studied too. But it's that magnetic field which gives the sun its character. And it turns out that the way stars rotate and the way that the gas of the star interacts with its magnetic field leads to a situation where you can build distortion and complexity in those magnetic fields. And the knock-on effect of that is that the magnetic fields end up being a bit like a sort of battery that stores energy that then can be used to power all of these activity events that I was mentioning earlier. So the magnetic field of our sun and other stars is a really crucial part of how they operate, how they evolve, the character they have. And so in our studies of the sun, we couldn't understand the sun if we weren't investigating its magnetic field. And that's what I'm interested in doing in my job at UCL.
Neil?
I was just talking about some of the most dramatic events that the sun history. Two pop up into mind. The Carrington event of 1859, and I think the Bastille Day event in July 2000. How powerful were those? In terms of the sun's anger, so to speak.
Yeah. So the 1859 event is a kind of not benchmark event, but it is the event that we take today to represent a kind of reasonable worst case scenario of what the sun can produce in the kind of timeline that is relevant to us. And so the Carrington event, as you said, is an event that happened in 1859, and it manifested itself as a series of solar flares. And in fact, the first time that a solar flare was observed on the sun was during this time frame. And the name Carrington event is named after Richard Carrington, who was the amateur solar astronomer who was going out day by day, drawing sunspots, making details about sunspots, configurations, locations, appearance on the sun. And he noticed that in early September 1859, suddenly there was these bright patches that appeared in the dark sunspot regions. And he saw this taking place just over a few minutes. There was a sort of a separate independent observation by Hodgson, also in the UK, and those two observations that corroborated each other became the first observations of a solar flare. What was also happening but wasn't known or seen at the time was that the sun was sending off a coronal mass ejection at the same time as the flare into the solar system. And that eruption, that coronal mass ejection, barreled through the solar system and reached the Earth. And when it got to the Earth, the coronal mass ejection impacted the Earth's magnetic field, and it interacted with it, it distorted it, and then through a series of knock-on events, there was changes to the Earth's magnetic field, changes to the atmosphere, this time manifesting itself as aurora, the production of the northern and southern lights. And they were so intense, those northern lights, and well recorded, along with an impact to the early communication networks in the form of the electric telegraph that was severely disrupted in many places. And so the Carrington event, because of its impact on the Earth, has become rather notorious in space weather and solar physics circles. So that lots of retrospective work has been done to work out the magnitude of the events on the sun, the solar flare, the coronal mass ejections, and to determine, actually through measurements that were made at the time, the impact on the Earth. And so it's thought that that size event might happen every 100 to 150 years. So that's why it's a kind of reasonable worst case scenario that space weather planning is based around today. And then the Bastille Day event from July 2000 was a kind of more modern day, very extreme event, not as extreme as the Carrington event, but was one that we were able to measure with spacecraft. And I remember it happening well. So I was early in my career in solar physics at this time. And I remember the SOHO satellite. So this is a ESA NASA mission that's has been studying the sun, was launched in 1995, collected data of the solar flare, of the coronal mass ejection, of high energy particles that came our way, and we were able then to monitor and understand how the sun's magnetic field was changing to produce this activity, because ultimately it all comes back to the activity. So you've got this very, impactful event from 1859, but very primitive data because we didn't have the same kind of technology. And then you had the event in 2000, and indeed many others that have taken place that we can now study with modern telescopes and space-based telescopes.
Now, one of the things I remember being talked about was, of course, the Maunder minimum, and how it was down to a lack of activity on the sun that caused the Thames to freeze so thick that they could actually roast oxen on the ice.
Yeah. So there's lots of kind of stuff out there about the Maunder minimum, which is a time when sunspots pretty much disappeared off of the sun for several decades. So perhaps around 70 years at the end of the 1600s, start of the 1700s. So we always have to ask ourselves, well, did that really happen, or were there just fewer observations of the sun? Maybe sunspot observations went out of fashion scientifically and people weren't monitoring the sun, but I think that wasn't the case. And there's been a revisit to these data sets and a sort of global project that has gone back and looked to make sure that it was actually a time of low solar activity rather than a time of lack of interest in solar activity. So I think we can really take it to be the case that during this Maunder minimum time, sunspots pretty much disappeared off of the surface of the sun. So that's telling us that the sun's activity level dropped accordingly, because sunspots are the regions from which you get solar flares and you get lots of coronal mass ejections. So that happened at the end of 1600s, start of the 1700s. And around the same time, there, as you said, there were times when the Thames froze over. And so this has kind of caused people to think that maybe there's a link between the sun's overall activity levels and weather on the Earth. And it's a very sort of complex area to talk about in a very sort of simplistic way, but I think there are different things to bear in mind. So one is that over the solar cycle, so as the sun goes from minimum to maximum in its activity levels, the amount of total light that's given out by the sun only varies by a fraction of a percent. So it's not a very big variation. So it's not as if we can say, there's a significant variation in kind of heat received by the Earth that then might have a knock-on effect to weather and temperatures on the Earth. That's not the case. What seems to be the case is that during the times when the Thames froze over, there were cold periods, but only in Northern Europe rather than globally. And so people are now thinking about there might be mechanisms that are linked, that are caused by changes in subsets of the light given out by the sun. So not its entirety, maybe a part of the ultraviolet part of the spectrum, for example, and that the way that variation in energy is then received by the Earth might set up or might influence global wind patterns. And those global wind pattern changes might move where the jet stream is. And the movement of the jet stream might affect winter temperatures in Northern Europe. And those lower winter temperatures in Northern Europe might cause the Thames to freeze over. So it's still, as far as I know, a really interesting area of research, but one in which the mechanisms are so complex that we don't have sort of clear answers at the moment. But I know it's appealing for some news articles to talk about, oh well, if the sun reduces in its activity levels, it causes global cooling. But that's not the case, and it's the sort of impact of the sun is complex and is still under investigation.
And does it have a longer cycle as well as the 11-year cycle? Is there any other pattern emerging from these kind of events, or have we not had enough time to study it?
Yeah, it's a good question. So there are longer term cycles. I think we always focus on the 11-year cycle because it is such a nice time scale over which we can study the sun. So I mark my career in solar physics in how many solar cycles I've been studying the sun. So I think I'm sort of just starting my third solar cycle now. Okay. But there are longer term cycles that can be picked up in various different data sets. And so I think it is more correct to think about kind of overlapping cycles. But again, all of those sort of, I don't know, I'm not sure how many it's like 2 or 3 different length scales of cycles have been detected or proposed that overlap each other. And what's really interesting to me is then variations of the solar activity across these different cycles need to be explained by what we call the solar dynamo. So the solar dynamo is the process by which the way the sun's fluid moves influences the evolution of its magnetic field. And so, for example, on the 11-year solar cycle, we need to understand how that sort of ebbs and flows over that time scale. And then you have to be able to take into account that there are these other longer term cycles as well. But all of those studies are really challenging because they are related to processes taking place inside the sun. And so we've seen really great progress over the last years to model the sun's dynamo. And there's been a lot of work that's been, I think, focused by international efforts to predict what the next solar cycle will do. So how large will the cycle be? How many sunspots will there be on the sun? When will cycle maximum be reached, for example? And so there's been great work sort of moving towards getting this physics-based understanding of what's happening inside the sun to explain the 11-year cycle, motivated by a prediction. And I think sort of techniques now are sort of starting to come together and show real fruit, bear real fruit.
I'd just like to ask, just from my own point of view, what made you particularly interested in the sun? Was it something you started in college, or was it something you've always been interested in since a child?
Yeah, well, it was something I came to at university. So I think I never really, thought too much about what the sun is as a star. It's an object that, in a way, is sort of hidden in plain sight because it's so bright and so dazzling. You don't look at it, you can't look at it, yet it's so familiar on the one hand because it's there every day and we all rely on the sun. So it was kind of a big moment for me when I was an undergraduate and I went to the Crimean Astrophysical Observatory, and we went there as a group of undergraduates to use telescopes at that observatory and do other studies. But while I was there, there was this lady who ran a solar telescope, and we, on the tour, got to go and have a look at that facility and look through the telescope at the sun, and obviously using special filters and special techniques. But it was such an eye-opener to actually see our local star and see structure in the atmosphere. So we were looking using a hydrogen alpha filter, which you may very well have looked at the sun through, because they're accessible. Astronomical societies will have people with telescopes with these filters. And I was so amazed that our local sun was so structured and interesting, and that kind of set me on a path to wanting to understand what was going on. And I think also the fact that the sun is so visual and so sort of aesthetically interesting, that also drew me in as well. So it was beautiful to look at, and it was scientifically like a curiosity. And I mean, I couldn't believe it when I realized that, or when I found out that actually you can have, a career researching the sun. And what's been nice then is to also realize that, the ways in which the sun impacts us. So it is on the one hand a real joy from a sort of scientific discovery point of view, but it's also a real joy because it can bring relevance to things like space weather forecasting and impact on our society.
Now, you wrote a book, 15 Million Degrees, A Journey to the Centre of the Sun. Could you tell us a bit about the history behind the book?
So that was a really fun thing to do. So I'm always keen to lift the lid on research, talk about what we're finding, but also show how we're doing it, who's doing the work. And when I had an opportunity to write a book, I thought, yeah, I should do this. And oh my goodness, it took me several years to write. I think I wrote twice as much as I actually needed to. My editor said, no, Lucie, you've got to cut this down in size. And I just had all these stories I wanted to share. But what was really nice was to be able to tell the history of understanding and studying the sun. And what I wanted to convey was, at the start of the podcast, as I introduced myself, I said, I'm a solar physicist. But one of the things I wanted to do in the book was convey that, solar physics in itself isn't really a thing. It's just physics. We use the same physics that you learn at school, you learn at university, physics of light, physics of, forces, electromagnetism, it's just physics applied to the sun. And so it was really nice to be able to talk about the history of discoveries in physics and how they then slowly opened up doors to studying the sun. So, for example, when I mentioned earlier about the sun having a magnetic field, as soon as that discovery was made, which was enabled by studies in the laboratory of what happens to charged particles when they move, how do we detect a magnetic field at a distance, all these things came together to then enable George Ellery Hale in the US to build a telescope that had an instrument on it that was able to detect a magnetic field at a distance and realise that sunspots, and by extension the sun, was a magnetic object. And that really started solar physics back in 1908. So it was nice to be able to talk about the history and the people who had made these developments and what the developments were. But then it was also nice to be able to talk about my colleagues and what they were doing, and what kind of contemporary solar physics research is, in a way that I can't really do in a talk or in a podcast and so on, because there's so much there. So it's nice to be able to talk about what's happening in my group at UCL, what's happening in the kind of wider community, talk about what we're doing from looking at the sun. So I'm an observational solar physicist, so my area is expertise is understanding instrumentation, understanding the data we get, and then using those data sets to answer the questions I have. But other people have other approaches. So I talk in the book about modelling approaches. So the people who have, codes that they've written to reproduce the sun's magnetic field, and then they can do experiments on those magnetic fields on their computer to try and mimic what the sun's doing and find out which theories are correct and which sort of stand up to scrutiny. So that was really nice too. And there's a bit in there about space weather as well, about the instruments we use, the spacecraft we use. So yeah, it was a really great thing to write.
also remember, I think several years ago now, when Comet Ison was about, I remember you going to an observatory. I think Alan Fitzsimmons was there and Pete Lawrence was there to see Comet Ison. It just shows you the power of the sun when it can destroy comets as they approach them, doesn't it, as well?
Yeah, that's right. Gosh, you got a really good memory. Yeah, we went out to the Canary Islands, and Alan Fitzsimmons came. So he's at Queen's University Belfast, and he's been studying comets and objects, small bodies in the solar system for a long time, asteroids and so on. And yeah, that's right. We went out to make a program for the Sky at Night on Comet Ison, and that was amazing to go and be able to see that comet from that location. And comets have played a really crucial role in studying and understanding the sun, because cometary tails were the first indication that the sun was sending a stream of particles into the solar system that we would today call the solar wind, and as we were talking about earlier, flows out to form the heliosphere. So cometary tails were were hypothesized to be formed by an outflow of particles from the sun interacting with particles that were given off by the comet. So comet tails point away from the sun no matter how the comet is moving for that reason. And then so that kind of hypothesis was established. And then in the late 1950s, Eugene Parker came up with a theory a theory that showed the sun had an expanding atmosphere that was producing the solar wind. So, and actually that's why the Parker Solar Probe is so named, because the Parker Solar Probe is studying the sort of solar wind as it leaves the sun. So it's a big, sort of thank you to Eugene Parker for the work he did in his theory. And then in the early 1960s, once the space age was beginning and we had spacecraft that were able to leave the Earth's magnetic field and get out into the space between the sun and the Earth, the solar wind was detected directly. So that gave the observational validation of Eugene Parker's theory and explained then why cometary tails are as they are. So, cometary tails can be influenced by photons of light coming from the sun, but they're also influenced by these particles that flow from the sun in the solar wind, sort of having a push on the particles to push them away from, produce the tails that point away from the sun. From the comet.
If anybody who's been listening to the podcast wanted to get started in solar physics, what would be the best way for them to go about it?
Yeah, good question. So I would say, at school level, study physics and do as much as you can. So GCSE physics, A-level physics, but also maths as well. And then coding is another key component. So I use one particular piece of software, but Python is a really good free piece of free code to use that lots of my students use now, and it's kind of the one of the way of the younger generation. So I think physics, maths, and computer coding are the three things, and that would then enable you to do the right courses at university, and then that would enable you to take on postgraduate studies in solar physics as well. But otherwise, see if you can get to look through a solar telescope. So find your local society who will have the kits and will be able to advise you on how to safely look at the sun. See what filters you might be able to look at the sun through. So maybe it's a white light filter that enables you to see the photosphere, so the visible surface of the sun and the sunspots. Maybe it's a hydrogen alpha filter that will enable you to see filaments in the atmosphere of the sun, these sort of dark snake-like features. Or maybe it's a calcium filter that you'll be able to sort of see structure in the sun's lower atmosphere, and then you can use these different wavelengths of light, these different filters, just to see how different the sun looks in these different wavelengths, and I think that's a really exciting thing to be able to do. And then you can go back, month after month, year after year, and see how the sun varies in time because of the solar cycle. And then you can also link up what you're looking at directly through the telescope to data sets that are freely available on the internet. So for example, you can go to NASA's Solar Dynamics Observatory website, and then you can look at the sun in other wavelengths of light, and you can see, how did that region that I saw directly with this ground-based telescope, how did it look from a space-based telescope in a different wavelength of light? And you can sort of start to build up this three-dimensional atmosphere of the sun.
Just wanted to ask myself, I know obviously you study our local star, but do you have a favourite? I mean, there's so many different types, but is there one that you look into and you're like, I'd like to know more about that one?
Oh, another star, you mean?
Yeah, sorry, another star.
Yeah, it's a good question. I think there was a very massive star that was discovered by a team at, I think it was the University of Sheffield. I hope I haven't got that wrong. And I forget the name. Other stars in the catalogue, in the catalogues that they're listed in, don't necessarily have a good name, but it was something like R1365 or something like that. And it was the most massive star discovered so far. And the hypothesis was that it was even more massive when it first formed, but it had lost some of that mass over time. And I would love to know more about that star. Yeah. How did that form? What's it like? What's its activity levels like? And how will it evolve in the future? So I think it's so massive that when it dies, it will completely tear itself apart and nothing will be left. But I thought, that to look at something so different from our sun would be really, really interesting.
I just read a book recently by another astronomer called Emily Levesque. I don't know if you know her. And she's talking about the practicalities of astronomy. And, when she started, she had to climb up into a telescope, sit there in the cold all night, and there was no facilities for women, like for the toilet. Yeah. And I'm just wondering, have you noticed differences in technology over the years in viewing the sun?
Yeah, I really feel for the women who had to go through that, and I've heard lots of stories of a small number of stories from the small number of women, I should say, who were there in those early years. It's amazing that there weren't even the facilities for them. It was so incomprehensible that women would be there at the observatory that they didn't have basic facilities like a toilet. Yeah, I have noticed changes in technology, certainly, and space-based and ground-based. So I think Parker Solar Probe and Solar Orbiter are two examples of that we're now at a point in time where spacecraft can be engineered and heat shields can be designed and built that protect the spacecraft at those close distances to the sun. But we've also got very complex, significant new ground-based telescopes being developed, like DKIST in America, where new instruments are being built that will allow us to measure. We talked a lot about the magnetic field of the sun, and it's more straightforward, although still complicated, to measure the sun's magnetic field in its surface layer in the photosphere. It's much harder to measure the magnetic field in the atmosphere that extends above that surface layer, but DKIST will be able to do that. And there are a series of very complex instruments on that ground-based telescope in America. So I think they're kind of good examples of how things are progressing. And then hand in hand with that, you've got developments in computing, in data storage that allow us to gather more and more data at higher and higher resolution. So as an example, when I first started in solar physics, I was using data from the Yoko, the Japanese spacecraft, and SOHO, the European/American spacecraft that we talked about earlier. And say for example, you might have image sizes that are like 500 pixels by 500 pixels. And then, more recently, we've been having images that are like 4,000 pixels by 4,000 pixels. So massive, increases in spatial resolution. And then going hand in hand with that, we might be getting images of the sun, once every 12 seconds from the Solar Dynamics Observatory. So we can see in much more detail with much higher temporal cadences to understand how smaller scale features evolve, how faster processes that are taking place in the sun are working as well. So I think there's all the sort of the progression of all these different aspects has been really important. I'm sort of reaching back into my memory now, because I think when I first started, 2 solar cycles ago, the PhD students before me, they didn't have their own computers. There were computers that were shared. And now, of course, it's completely unthinkable that you'd have to wait for your turn on a computer to do the calculations and data processing and whatnot for you. Now, this is our tool. We're all sat in front of our computers, or maybe even, more than one computer. So, yeah, it's been a massive, massive increase, which has really, really reaped its rewards.
Can I just very quickly, just to get back to Solar Orbiter, are you aware of, just to get the little plug in from Ireland here, of our little country, that an Irish company called Embio came up with a solution for the heat shield for Solar Orbiter with Solar Black?
Yeah, absolutely. So I have a little piece of Solar Black that they sent us. Yeah,
I have it here beside me.
It's a brilliant material, isn't it? And it is so, it's such a great story that, that this company in Ireland that were looking at, I mean, you probably know more details than I do, about that they were working, was it medical surface or medical devices?
For implants to be attached to metal, so that it would, and they were going to cover it with burnt bone.
Yeah.
And which also went back to the time of the cave paintings, and they discovered that the same kind of burnt bone that they used then had bonded with the rock and became the rock, and it doesn't stretch, it doesn't change colour or anything. And somehow, I don't know how they made the leap, but discovered that this was the stuff that would protect the spacecraft.
Yeah.
It's absolutely fascinating.
Yeah, and it's exactly that kind of technology development that means Solar Orbiter can fly, because if that solution hadn't been found and the spacecraft couldn't be protected from the heat of the sun and the onslaught of the particles at that close distance, then Solar Orbiter wouldn't be able to fly. So Embio with their contribution is enormous. So Solar Black, and the fact that it's made from like charcoal cow bones is kind of it's this really interesting, fascinating story. Massive contribution.
We have plenty of burnt cow bones as well, so recycling in its best.
So it's nice to have a little bit that you can sort of keep on your desk and have a look at. It's like little reminder.
And it's so thin. I mean, it's just like a hair. It's so very, very small, isn't it? Amazing how strong it is.
Yeah, and the fact that this material is able to, as you say, last in the extremes of space. It doesn't sort of the particles don't come off. It doesn't get statically charged in the flow of electrically charged particles from the sun. It takes in the heat of the sun and sort of safely then means you can sort of dump it out the side of the spacecraft. So it's a really remarkable material.
Neil, you've been very quiet. You got anything else you'd like to ask?
Well, just talking about our sun, most stars that we look at in the sky, they're in pairs, or there's triplets and things. Has our sun possibly ever had a sibling, or are there any candidates that are quite strongly linked, perhaps?
Yeah, so it is one of those curiosities that why is our sun not in a binary? Why doesn't it have a kind of counterpart? But there was a study some years ago now that looked at a star that showed it could have been made from the same primordial material as the sun was, and was moving in a way that suggested in the past it was closer to the sun than it is now. And that star was proposed to be not necessarily a binary, but another star that would have showed that there were two that formed from the sort of same cosmic proximity. And I thought that study was really interesting in kind of opening up the possibility that maybe our sun wasn't a lone star that formed, that there was a second one, but that over the eons and interactions, the other star is now heading off away from the sun.
Well, I have to admit, the thought of sharing a solar nebula is an intriguing one, and it would be nice to find out the actual truth of the matter. But I suppose we're going to have to wait for quite a while. Certainly, I suspect, until we can actually get out of the solar system ourselves.
Yes.
Yeah, it would be nice to be able to, kind of have our wish list of all the data sets we'd like to have and have them all appear. We have to work hard.
A few more cycles before we get what we want to get, I'd say.
Yeah, but we'll keep going, and future generations will collect the data.
On we go.
Lucie, you've been doing wonderful work popularising astronomy, and for a woman to do this, it's great to see. Are you noticing more women getting involved now as time goes on? Or, like your students, would there be more women now than there would have been, say, 20, 25 years ago?
Yeah, I think so. I think anecdotally, the cohorts of students I see coming through now are, there are many more women coming through in astrophysics, and actually in solar physics, I think in particular. I think in physics in general, I'm not sure what the sort of undergraduate numbers have done recently, but I know at A level, there's been a sort of stubborn stick at women only making up 20% of A-level physics students. So that number seems to be a really hard one to shift. But in terms of at least who I see in my immediate community, there's many women coming through, which is great, and in all subjects in space science, in astrophysics. So, for example, in my department, obviously we do solar physics, we do planetary research, exoplanets, galactic studies, stellar studies, and it's really fantastic. And I think the other thing that I really am encouraged by is that PhD students I see coming through now, they're all really naturally gifted communicators, and it's sort of second nature to them to want to be talking to different groups about space science and enthusing with different groups. And that, I don't know, why that's the case. Is there something that happens in that there's just sort of more discussion in the media, or is it something about the school curriculum? But all the students I meet now want to be out there talking to other people about their research and space science in general.
I would think... Sorry, Anne, go on.
No, I just think that's marvellous. I'm so delighted to hear that.
I was going to say, perhaps it's also with the fact that we have social media more so now, and we have the internet. It does allow people to actually speak about these subjects much, much easier.
Yeah, you're right. So maybe there are sort of those communities that form. So it's not just about a geographical community. You find the community that shares your interests, and then you can communicate and share and enthuse, and that there are other people out there. So I'm really pleased. I've had meetings recently with our new cohort of students, and so many of them are brilliantly wanting to. Well, in fact, they've already very active in public engagement and communication, and they want to carry it on during their PhDs.
That's wonderful.
Now, as I remember, and I could be wrong, you are also chief stargazer over at the Society for Popular Astronomy.
Yes, that's right. So that's a great pleasure. I mean, the Society for Popular Astronomy, I just think is an amazing organisation, so dedicated and talented and knowledgeable, as you know, are many astronomical organisations around the country. I'm always really impressed at how people give up their time to support others and introduce astronomy to other people and give advice and so on. So it was really, you know, an honour to be able to sort of help in some small way or support them in the work that they do. And it felt very natural then to be able to support younger generations coming into astronomy. So there's a special part of the publication that's all about young people wanting to, or who are getting into stargazing, and different activities are written up for them. We love to have drawings and any images that are taken sent to us. So, and I think it's really important that these organisations, exist. And Society for Popular Astronomy is just a great gateway into observing and giving people a sense of community and advice on what to do.
Where do you see solar physics going in the next few years?
So I think that it's becoming more able to look at smaller scales on the sun, so that we can connect up across the size scale spectrum. I think also there's an element of sort of focused science questions. So, for example, in the past, we've had, let's say, satellites that have looked at the sun that have given us very routine observations. So, like the Solar Dynamics Observatory kind of runs a standard program of observation. We do have other satellites like the Japanese Hinode mission, where we can say, right, this telescope will look at this part of the sun with this observation program at this time. And we led one of the telescopes on board that spacecraft. The telescope's called ICE. And I really like that telescope because you can say, right, these are the targeted, focused observations we're going to take. And I think with missions like Solar Orbiter, we're sort of coming back to that way of working, because Solar Orbiter's orbit around the sun means we can't just gather very, very regular data, because the spacecraft is often too far away for us to have a good contact with it and download lots of data. So we have to be very focused. We want to answer this particular science question by doing this particular observational sequence. So there's a kind of change in the way that we're thinking and the work that we'll do. And people often call Solar Orbiter like an encounter mission. So they see it as analogous to, say, a planetary encounter, where you have limited opportunity to collect data and images. And so you need to be very focused and plan well in advance as to what you're going to do.
Well, Neil and I have a question that we ask on our other show, Comet Watch. If you had a blank check and you could organise a space mission, what would you do with it?
Oh, yeah. Well, for me, I'd have to say I would have a mission that looked at the sun's magnetic field, because that's at the heart of who the sun is and what the sun does. And I would like to have lots of data. There's the blank check. So I would have a kind of swarm of spacecraft that would see all around the sun. So it wouldn't just be about looking from the Earth's perspective, and it wouldn't be just about looking from the plane of the planets around the sun. I'd want to see over the poles, over both poles, and be able to see the three-dimensional or the whole sphere of the sun. So I don't know exactly how many spacecraft I would need. Maybe I would want 1, 2, 3, 6, 7, 8, something like that would form this kind of, web around the sun and give me constant coverage.
Have 42,000 around us at the moment, or they will do.
Yeah.
So maybe something multiplied by that.
Yeah. yeah. If we could just have some of that technology.
Dyson spheres kind of thing then, but you have a blank check, so.
Yeah. Oh, that's the dream. That would be fantastic. And then hopefully I'll be able to, employ lots of people to analyse the data as well.
Yeah. That'd be no problem with the blank check.
Neil?
Yeah, well, I know because we're getting close to time now, aren't we? Because the final question now is solar cycle number 25, which is the one we're in now. What are your predictions, Lucy, for what we're going to see, the progress to sunspots and things like this?
Yeah, so I think I'm going to sort of give an answer that's based on what the consensus seems to be in the community. I mean, it's not to say that, I say consensus, not everybody agrees, but that's a good thing about science when you have lively debate. But it seems to be that the predictions are pointing towards a solar cycle which is not too dissimilar to cycle 24. So it won't be a large cycle. It'll be a kind of moderately sized cycle, peaking in a few years' time. So, yeah, it feels a bit like the status quo is going to be maintained, which is interesting because it wasn't necessarily thought to be that way, sort of a decade ago. There were thoughts that the sun was getting quieter and quieter and that subsequent cycles would get smaller and smaller in size. But it looks to be that cycle 25 won't be too dissimilar to the one that we've just left.
Excellent.
Well, thank you very much for coming on the show. I know it's getting late for all of us. We would love you to come back at a later date if possible, and so we could talk some more, because we could go on all night, I suspect, about the sun.
Yeah. I think we could. I think all of us could talk for quite some time about our lovely local star. But thank you very much for having me.
Great,
Thank you, Lucy.
Thank you, Lucy. It was wonderful to meet you.
Take care.
Take care. Bye-bye.
Bye.